This is MAT 2020 lecture 41. Today we will begin covering section 11.10. It's going to take more than one lecture. I want to remind you last time of a particular series that we derived, infinite series, for tangent x. So we saw that we looked at x minus arctangent of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. Now this actually converges. Radius of convergence of the right side is absolute value of x less than 1. So let me write r equals 1, r for the radius of convergence, which means that on the interval from -1 to 1, it's going to converge on the open interval. But what about the endpoints of the interval? So if we take x equals +1, the right-hand side is 1 minus a third plus a fifth minus a seventh, and so on. And this is an alternating series. And this alternating series is bounded, and the limit of the terms is 0, absolute value of the terms is 0, so this converges. Similarly, if x equals -1, it also converges, same reason. So in particular, we can look at arctangent of 1. Now arctangent of 1 is pi over 4. But if we plug it into the series, which converges, we're going to get 1 minus a third plus a fifth minus a seventh plus a ninth, and so on. So we've got an expression for pi over 4 as the alternating sum of the reciprocals of all the odd numbers. And so this is actually very remarkable, I think, because the left side is pi over 4. Pi is a rather complicated number, and we've expressed pi over 4 as an infinite series using very simple numbers. Okay, I thought I would just point that out now. So what I'd like to do now is really move on to section 11.10. Okay, so section 11.10 is about so-called Taylor and Maclaurin series. Taylor and Maclaurin were names. Maclaurin series are a special case of Taylor series. So here's the basic problem. So here's the problem. Given a function f of x, when can I express it? Is it a power series centered at A? When can I express it as a power series centered at A? In other words, when can I write f of x as c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on. So we have to figure out what the values of the constants, the coefficients, are in front of the x minus a to some power. So here's how you can figure out what they are. So first of all, let's take evaluate the expression. If it's going to be true, f of a must be equal to c0 plus nothing else. All the other terms actually vanish. So now we know that c0 is f of a. So let me write it like this. We're trying to solve for these constants. So now let's compute C1. How do I do that? Well, one way to do that is to differentiate the expression. So we'll get f prime of x equals C1 times the derivative of x minus a, which is 1, plus 2c2 times x minus a squared plus 3c3 times x minus a, I'm sorry, not x minus a squared, but x minus a to the first power. So x minus a squared plus 4c4 x minus a cubed, and so on. So if we evaluate that at x equals a, we get f prime of a equals c1. So I'll write that as c1 equals f prime of a. Box it off. Okay, now let's take the second derivative. Something interesting is going to happen now. So the second derivative, f double prime of x is given by 2 times c2 plus 2 times 3 times x minus a plus 3 times 4 times c4. Oh, there's a 2 times 3 times c2 x minus a plus 3 times, I'm sorry, I messed that up. It should be c3. 3 times 4 times c4 x minus a squared. Let me write one more term. 4 times 5 times x minus a cubed, etc. Let's now evaluate this at x equals a to get f double prime of a equals twice c2. In other words, c2 is equal to f double prime of a over 2. Let me box that off. Okay, let me do one more derivative. So the third derivative of the function f is 2 times 3 times c3 plus 2 times 3 times 4 times c4 x minus a plus 3 times 4 times 5 x minus a squared, etc. So now let's evaluate it at x equals a. So we get f3 of a equals 2 times 3 times c3 So that tells me, I'll write it on the right-hand side, that C3 equals the third derivative of f evaluated at a over 2 times 3, which you should think of as 3 factorial. And in fact, this was a 2 factorial in the previous green box. And in general, you can see the pattern. The pattern is this. Let me clear the screen. So in general, the nth coefficient of the expression is n, the nth derivative of the function evaluated at a divided by n factorial. So that's the general formula for the coefficients if the function can be expressed as a power series. So, so the conclusion, let me make the conclusion so far. If f of x can be expressed as a power series at a, centered at a, then the coefficients c sub n are given by the nth derivative of the function evaluated at a divided by n factorial. That's the conclusion. So, and so what you get is f of x equals c0 plus c, not c0 anymore. It would be f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus the third derivative of f evaluated at a over 3 factorial times x minus a cubed, and so on, dot, dot, dot. In other words, we can write this in sigma notation as the sum n goes from 0 to infinity of the nth derivative of f over evaluated at a over n factorial times x minus a to the nth power. Okay, so that's the formula I wanted to derive. It does not tell us, though, when the function can be expressed as a power series. It just says if it is expressible as a power series, then these are the coefficients of the power series. These are what they have to be. So we have to answer the question really still of when a function can be expressed as a power series at x equals a. But before I do that, I want to do a single example. So here's an example. Let's look at f of x equals e to the x. So and let's take a equals 0 as where we're going to center our power series. So all the derivatives of e to the x are e to the x. So fn of x is e to the x. Therefore, so c sub n is e to the 0 over n factorial, which is 1 over n factorial. And therefore, the series is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So in other words, the power series is summation, n goes from 0 to infinity of x to the n over n factorial. So the conclusion here, if e to the x can be expressed as a power series at x equals 0, then e to the x must be equal to, at least in some neighborhood of, for some values of x near 0, summation x to the n over n factorial, n goes from 0 to infinity. Okay, so now but we don't know, there's an if here. The if is right here. And we need to answer that if. Maybe it's not expressible. So this is where where we have to do some work. Okay, so there's the so-called nth Taylor approximation to f of x at x equals a, and that's given by the following expression. It's t sub n of x. It's going to be a polynomial in x minus a, so it's going to be given by the sum k goes from 0 to n of f's k of a over k factorial times x minus a to the k. In other words, we truncate the series up at degree n. So this is going to be a polynomial in the expression x minus a. Okay, there's also, so this is the nth Taylor polynomial, the nth Taylor approximation, and there's also the remainder, the nth remainder, which is kind of an error term. The nth remainder is given by the difference between your function and the nth Taylor approximation. So this is the difference between your function and this polynomial. So in other words, so f of x can be expressed as the nth Taylor polynomial plus the remainder term. Okay, so in any case, here's the result I want to mention. So this is the first theorem. So we could also note if n equals infinity, we have t infinity of x is the sum n goes from 0 to infinity of the nth derivative at a over n factorial x minus a to the n. This was the power series that we described before. So this is a power series. Okay, so here's the statement I want to make. The statement is this theorem. If the limit as n goes to infinity of r and of x equals 0 for absolute value of x minus a less than r, that is on the interval, open interval a minus r, a plus r. So this is the interval centered at a, where you look at points within distance r. So if this is true, if this remainder tends to 0 in n, then f of x is equal to this, it's series t infinity of x on a minus r, a plus r. So this is the basic result. So we need to find criteria for deciding when this is true. So when is this true? When does this happen? That's the question. So now we get to an important result, which tells us when this happens. Okay, so let me state it. It's called Taylor's inequality. Okay, so it goes like this. Suppose the nth plus first derivative of the function f of x, we take its absolute value. Suppose it's bounded by some number n on some interval, on some x minus a less than some number. Let's call the number, the book calls it d. It's in other words, on a minus d, a plus d. Okay, suppose this is true on some interval. Then the statement is that the absolute value of the error, that is this remainder, is at most m times x minus a absolute value to the n plus first power over n plus 1 factorial on the interval a minus d, a plus d. So this is the so-called Taylor inequality, and this can be used in some cases to show that the Taylor series is going to this infinite series coincides with the function on that interval. So so this is the basic result, and I want to just illustrate it in the remainder of the lecture for the function e to the x. So let me do that. So remember, before I erase the slide, we're looking for a bound for the nth plus first derivative. Okay. So let's look at, in order to proceed for e to the x, so let's return to looking at e to the x. Okay, so so in this case, we know the nth plus first derivative of e to the x is e to the x. And now we know that a equals 0 in this example we did before. So we're looking at some interval between some numbers minus d and d. The role of d will become clear as we proceed. So d is just some positive number. D is any number for now, greater than 0 for now. Okay, so now according to the Taylor inequality, Rn of x, absolute value, the nth remainder, is at most what? Well, we need to find a bound on between minus d and plus d of the function e to the x. That's the n plus first derivative. It's clear that e to the x is an increasing function, so e to the x is going to be less than or equal to e to the d on the interval minus d plus d. So, and that's true in that. And by the way, we have to take absolute value, but e to the x is always non-negative. So in other words, the m, we can take m equal to e to the d. So then the application of Taylor's inequality says that that the nth remainder is at most e to the d times x minus a 0 to the n plus first power over n plus 1 factorial. Okay, so now what I'm going to do is I have to analyze what's going on with the right-hand side. Okay, so here's a fact. The limit as n goes to infinity of x to the n over n factorial is equal to 0. Why is that true? Well, here's a reason. Here's a dumb reason. If we look at summation x to the n over n factorial, that's a power series. And the ratio test tells us this is a power series. And the ratio test says it implies it converges for all x. The radius of convergence of this series is infinity. So therefore, since the series converges, that implies the limit by the divergence test of x to the n over n factorial had to be 0. So that's what we wanted to show, this fact. Okay, the reason why this fact is important is we can apply it to the expression that I'm circling in yellow. According to that, let's look at that expression. So then the limit as n goes to infinity of e to the d absolute value x to the n plus 1 over n plus 1 factorial is certainly going to go to 0 because we can pull the constant out. So this is going to be 0. So this is going to tend to 0. And Rn of x is bounded below by 0, so we can use the squeeze theorem. That'll imply that the limit as n goes to infinity of absolute values of Rn of x is 0. But if that's true, that'll imply that the limit of the unabsolute valued terms, Rn of x, had to be 0. We actually proved that with sequences, back in sequences. So if we had a sequence and we took the sequence of absolute values and that limit converges to 0, then the original sequence converges to 0. So therefore, that's what we needed to know, that the remainder tends to 0. And so what is the conclusion then? The conclusion so far that the limit as n goes to infinity Rn of x equals 0 on minus d plus d on this interval. But d was arbitrary, but d was any number. It was any number you gave me. So therefore that implies that the limit as n goes to infinity of Rn of x is 0 always for all x. So in other words, that implies that e to the x equals t infinity of x. That is the sum of x to the n over n factorial for all x. So let me just conclude today with the following fun fact that comes out of this. The fun fact is that we can set x equal to 1, and the left side is e to the power of 1, which is e, is given by this series, which is 1 over 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc. So the sum of the reciprocals of the factorials, in fact, you could put 0 factorial here if you want, because 0 factorial is 1, gives you this very strange number e as a sum of reciprocals of all the factorials. That's an amazing formula. Okay, so we got two amazing formulas today. One involved pi over 4, which was an alternating sum of the reciprocals of the odd integers. And we have also a formula for e. This is kind of cool, don't you think? That's it for today. Until next time.